Hey everybody, in this video we are going to go over a 15-question multiple choice exam based on Unit 7, the states of matter. Now all these questions come from the Chemistry Olympiad, so they will be a bit challenging, but I'm sure that we will be able to do this. So let's look at number 1. The critical point of carbon dioxide is 304 Kelvin and 73 atms. Under which conditions is carbon dioxide a liquid? So they give us two conditions, and at first this might be confusing because we don't have any diagrams, but why don't we just draw our diagrams? So let's make our diagram, and if you remember, the solid state of carbon dioxide is denser than the liquid state of carbon dioxide, so the slope of the solid liquid boundary will be positive. And the phase diagram might look like that. And if you remember what the phase diagram looks like, you might remember that the critical point is located somewhere over here. And then we have like this little box which labels the supercritical fluid. So that is where the critical point is, and it says that it's at 304 Kelvin and 73 atms. So it says which condition is it a liquid? So our liquid is over here, and let's think about this. So the first condition is 303 Kelvin and 73 atms. So isn't that just to the left of the critical point? And that will be 303 Kelvin. And if it's to the left, we clearly see that it's in the liquid. So 1 will be correct. Now, is condition number 2 going to give us a liquid? 305 Kelvin and 74 atmospheres worth of pressure? Well, let's think. So 305 is to the right, so it's over here, and instead of 73 atms, it's 74 atms, so it's going to be a bit above, like over here, and that's going to be 74. Now that point's in the supercritical fluid section, so it's not going to be a liquid, so therefore our only answer will be 1 only. Number 2, which set of characteristics describes a metal? Let's read the first one. Melting point 180 degrees Celsius. That's quite low, but it might be possible because 180 is still pretty high. It is soft and it is electrically conductive as a solid. Now this sounds like sodium to me, because sodium, as you might remember from video 7.6, is soft and it has relatively high melting point, but not very high. And we know that it's electrically conductive, so A might be our answer, but let's look at the other choices. Melting point 388 degrees Celsius, maybe. Soluble in CCl4, no way. We said that metals were never soluble unless they dissolve in mercury. Now let's look at C. The melting point 801, maybe. It dissolves in water to give an electrically conducting solution. While metals don't dissolve in water, only their ions dissolve in water, and we're talking about metals and not their ionic form. So because we are talking about metals like sodium, they don't dissolve in anything except for mercury, and because of that, it will not dissolve in water, so C is out. Now let's look at this. Melting point 1400 degrees Celsius, maybe. Insoluble in water, oh, of course. Has electrical conductivity that is low at room temperature but rises sharply as temperature increases. Now this sounds like a semi-metal to me, and not a metal, so D is out, and A will be our answer. Now let's look at number 3. Ammonia, NH3, has a high normal boiling point, negative 33 degrees Celsius, than its heavier congeners, pH 3, boiling point negative 88 degrees Celsius, or ASH3, boiling point negative 63 degrees Celsius. Which is the best explanation for this difference? So as you notice, N, P, and AS are directly below each other on the periodic table. So it says that this has the highest boiling point, this has the second, and this is last place with the lowest boiling point. So what might be responsible for this interesting trend? Well, let's read our responses. NH3 is trigonal pyramidal and polar, while PH3 and ASH3 are trigonal planar and nonpolar. Now, I don't think this is true, because if you draw out their Lewis structures, they will all look the same, so A is out. B. NH3 is much more acidic than PH3 or ASH3. Now, I don't think that something being more acidic, which means that it has a higher tendency to release protons in the form of H+. I don't think that has to do anything with the boiling point. That might have to do with reactivity, but boiling point, not really. NH3 experiences stronger LDF forces than PH3 or ASH3. Now, this is not true because ASH3 should experience stronger LDF forces since it has a larger electron cloud due to the high number of electrons it has, especially on the AS. So C is wrong. Now, what does D say? NH3 has extensive hydrogen bonding while PH3 and ASH3 do not. Well, this makes sense since NH3 can form hydrogen bonds, and these bonds are super duper strong, and it can form a lot of them because, you know, N has 3 H's and it has 3 opportunities to link and form hydrogen bonds. And because it can form lots and lots of hydrogen bonds, and these hydrogen bonds are very strong as well, then the boiling point for NH3 would naturally be a lot higher than its counterparts. So D seems legit, and now let's move on. Now, for number 4, we need a periodic table, and you're allowed to use that, so don't worry. Number 4, in which are the ionic solids ranked in order of increasing melting point? So this will be the highest, and this will be the lowest. Now we have 4 salts that we need to look at, and let's think about what factors cause ionic bonds to be stronger, and this will cause the melting point to increase. So there are 2 things, the charge, as well as the ionic radius. So let's look at the charges. So let's actually write this on the corner. KBr is going to be +1 and -1. NaCl is going to be +1, -1. NaF is going to be +1, -1. And MgO is going to be +2, -2. Now let's draw their ions. So K will be, well, actually before we start, let's actually do something special. So if you're in period 1, you'll have a small circle. If you're in period 2, you'll have a slightly bigger one. Period 3, an even larger one. And period 4, an even larger one. And this will help us determine the sizes of the ions by just kind of estimating it based on the period they are in. Now this works because all of these elements are in different periods, and that's why I'm doing this. So K is in period 4, so I have to draw it like this, and Br is also in period 4, so I gotta draw it like this. Now what about sodium chloride? Sodium chloride are in period 3, so slightly smaller. NaF, well, Na is this, and F is in period 2, so slightly smaller. And MgO, well, Mg is in period 3, so it will look like this. And O is in period 2, so it will look like that. So now we need to think about this in terms of the radii first. So let's measure the distance between the centers and determine which ones are the shortest. So the shortest ones are going to be this one and this one because you have 2, 2, 3, 3 here, while these ones are 3, 3, and 4, 4. So generally when you go down the period, you're going to have a larger atomic or ionic radius. So that's why I'm doing it this way. Using pictures is very helpful. So I have to compare these two. These two have the smallest ionic bond length, and because of that, they will experience the most attraction according to Coulomb's law, and because of that, they will have the highest melting points. So we have to compare NaF and MgO. So looking at these two salts, we can see that MgO has higher charges than NaF, and higher charges means more attraction according to Coulomb's law. So because of this, MgO should have the highest boiling point, and the answer choices, MgO has the highest boiling point only in answer choice A, so we could just choose A. And we're not just going to stop there because we want to learn, and if we want to learn, we gotta go through all of them. So sodium chloride is second place, so second place right there, And how do we compare these two? They have the same charges, but the ionic bond length here is shorter than over here, so that means that the melting point of sodium chloride will be higher than KBr, and that's reflected in answer choice A. So we're done with this problem, and let's move on. Number 5, a two-dimensional slice through the lattice of a crystalline solid containing two different elements X and Y is shown schematically and to scale below. What type of solid is it? Now this might be confusing, but basically you have a crystalline solid, which I'll draw as a cube, and someone took a slice of it, or a cross-section, and now you have this. So let's think about this. So it says it contains two different elements, X and Y, so let's just, draw the compound XY, and this could be a salt, it could be a molecular compound, it could even be a metallic alloy, who knows, right? Let's think about how this works. So, a metallic alloy such as FeCr. Now, alloys have their metallic atoms scattered randomly in the sea of electrons, so you wouldn't have an orderly combination of XY 6 times in an alloy, because that's just too perfect. So because of this, it should not be a metallic alloy due to its orderliness. Now, is it a molecular solid? A molecular solid like IBr would make sense, because if you think about it, IBr is going to be slightly polar because Br is more electronegative than I. So because of this, you have a bond dipole and a net dipole, so this is partially negative, partially positive. And if you think about it, how do polar molecules react to each other? Well, they form dipole-dipole forces, so it might look like IBr over here, partially positive, partially negative, and these permanent dipoles will, connect to each other, so partially negative, partially positive attract. And notice how this is XY and XY, and they're located like a distance away, just like in this image. So B is a plausible answer. Now, if you want me to label the partial charges, I could label this partially negative, partially positive. And as you can see, the partially negative attracts partially positive. And let me just erase that and show the dipole-dipole interactions. And yeah, that would make sense, because this would interact with that, and this might interact with that, and this might interact with that, and etc. Now let's look at our other answer choices before coming to a conclusion. C, an ionic compound such as lithium chloride. Now does this make sense? Let's try to draw this out. Li plus, Cl minus, and the Li plus would be here because they have to be oppositely charged, and Cl minus would be here. But that's not what's happening in this image, because first of all, there's spaces between them, and in addition, if you notice, the Cl and the Li have to be in the same position, but in this case, the Cl and the Cl, which I'll call Y, are in the same position, and this doesn't make sense, since if Y is negatively charged, and if this is negatively charged as well, why would they want to be in that orientation? Salts are supposed to have negative, positive, but since in this image it's going to be positive, negative, it won't make that much sense for this two-dimensional slice to be an ionic compound, so C is out. Now what about D, a network covalent solid such as SiC? Now the problem I have with this is that in a network covalent solid, there are covalent bonds, and these covalent bond lengths are typically around the same. And in this image, you can see that the distance between the X and Y here is like that much, while the distance between the X and Y here is like 3 times as much, and covalent bonds generally don't differ by that much. And because of that, I don't believe that this is a network covalent solid, and therefore the answer should be B. And B makes sense since the molecules are typically spaced apart. So, for example, the bond between the XY is a covalent bond, and it's pretty short. But the dipole-dipole interactions are typically longer, and that's why in this image you see that it's a lot longer, so it makes more sense for the answer to be B. Now let's take a look at number 6. One unit cell of a crystal containing elements X, Y, and Z is shown below. What is its formula? Well, we can look at this and see that there are 8 corner Y atoms, there are 6 face Z atoms, and there's 1 center X atom. So now let's determine the formula for this unit cell. So there's 1 center X, and remember 1 center is worth 1 atom, then there's 1 X. And there are 8 corner Y atoms, and each corner atom is worth 1/8 of an atom, so it's going to be 8 corner atoms times 1/8 for each, and this is equal to 1 Y atom. So we have 1 Y. And what about Z? Well, there's only 6 face atoms that are Z, and each face atom is worth half an atom. So since there are 6 face atoms and each of them are worth 1/2, there are a total of 3 atoms. So there are 3 Z atoms, so X, Y, Z, 3, that's B. And if you didn't understand that, I highly recommend watching video 7.5 because that accurately describes why I am counting corner atoms, for example, as 1/8 of an atom, or why I'm counting face atoms as half an atom for the unit cell. So let's move on. The boiling points of the alkali metals decrease from lithium to cesium. What trend is most closely related to the decreasing boiling points? So let's think about why the boiling points of alkali metals decrease from lithium to cesium, which means from the top to the bottom. So why do you think this happens? Well, let's think about what causes alkali metals to have high boiling points in the first place. They have metallic bonds, so it's going to be a sea of electrons, of course. Now, why would the metallic bond get weaker from lithium to cesium? Well, lithium is small, and cesium is gigantic, so the distance between the electrons and the center of the cesium atom will be pretty large compared to the distance between the electrons and the center of the lithium atom or its nucleus. And because the distance increases as you go down a group, the metallic bonds get weaker as you go down, and that's why the boiling points decrease as you go down. So what causes this? Let's see. Atomic radius? Well, we just talked about that, so that's probably the answer. Increasing atomic mass? No. Decreasing electronegativity or electron affinity? No. So our answer is A. Now let's take a look at number 8. Which aspect of metallic bonding best accounts for the characteristic malleability of metals? A. Metals have a few valence electrons. B. Metals contain a lattice of positive ions. C. Metals contain delocalized electrons. And D. Metals have a low electronegativity. Now, if you remember from the video, I said that metals are malleable because they are essentially just cations in a sea of valence electrons, and if you hit it with a hammer, all the cation is going to do is move away, and in the end, you just have a deformed metal. And the reason why it is able to deform this easily is because the metal cations are basically swimming in the sea of electrons, and the sea of electrons is kind of like a fluid that allows the cations to move around easily, and this accounts for malleability. So the answer is C, because the sea of electrons is just the sea of delocalized electrons, and delocalized just means that it's not like connected to one atom, instead it's spread around everywhere, and this makes sense since a sea of electrons just contains electrons that were once part of the atom, but they kind of just move around. So let's look at number 9. This one requires a bit of math. A metal with a face-centered cubic lattice has a unit cell edge length with A equals 380.3 pm and a density of 12.45 grams per centimeter cubed. What metal is it? Well, we have to think about what face-centered cubic means. This means that it will have 4 atoms per unit cell, and we talked about this in video 7.5, so go watch that if you don't know what I'm talking about. And let's think. So it gives us the cell edge length, which is 380.3 picometers, and we could easily convert this to 380.3 times 10 to the negative 12 meters, and we could go even further and turn it into centimeters. And to convert it into centimeters, we know that a meter, or more precisely 10 to the negative 2 meters, is in 1 centimeter. And when you multiply this conversion factor, you get 380.3 times 10 to the negative 10 centimeters. So this is very important because it will allow us to use density, since density involves centimeters cubed. So let's now find the volume of this unit cell, since I think that will be important. So the volume of a cube is just the edge length cubed. So 380.3 times 10 to the negative 10 cubed will equal, well, let's put the centimeters there, of course. So 380.3 times 10 to the negative 10 centimeters, and we have to cube all this, and I get 5.50 times 10 to the negative, okay, my screen's kind of lagging, 10 to the negative 23rd cubic centimeters. So I have a feeling that this will help me because I have volume and I have density. What can you do with density and volume? Well, you can multiply them. So we know that 5.50 times 10 to the negative 23rd cubic centimeters is in a unit cell, and we know that the density of this mysterious metal is 12.45 grams per cubic centimeter. And if we cancel these out, we can see that the mass of the unit cell, so we're not finding the volume anymore, we're going to find the mass of the unit cell. It's going to be 6.85 times 10 to the negative 22 grams. Now, we also know that there are 4 atoms in this unit cell, so that means that this mass has to correspond to 4 atoms. And you know what that means, right? If we divide these two, we can find the amount of mass in one atom. So let's get right to it. This number divided by 4 will give us 1.71 times 10 to the negative 22 grams per atom of this mysterious metal M. So we can easily turn this into moles of M by doing Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. And let's do that, 6.022 times 10 to the 23rd. And I got on my calculator that the molar mass of the substance is going to be 103.1 grams per mole. And look at that. Using a periodic table, I can easily find the identity of this metal. So I'm going to use a periodic table and look for which one is closest to 103.1. So it looks like RH is very close to that, and therefore C will be our answer, because RH, according to my periodic table, has a molar mass of 102.9, and this is very, very, very close to 103.1. So this was an interesting problem to do, but we did it. So now let's do number 10. Which of the following properties is not typical of metallic solids? A, high vapor pressure. Well, that's not typical of metallic solids, so A is our answer. Now let's look at the other choices. B, high coordination number of atoms in the lattice. Well, we didn't learn this, but the coordination number is simply the number of atoms attached to one atom. So for metallic crystals, remember that, for example, for the simple cubic, you have one atom connected to at least 3 of them, and there are much more, because if you remember, simple cubic, extends into the 3D plane, and this is just for a unit cell. There are more cubes going on in other places, so this atom over here is connected to a lot of things. And because of that, yeah, these metals will have high coordination numbers. So B is not the answer. C and D are just conductivity, and we know that metals have high electrical and thermal conductivity. So C and D are out, and A is our answer. Alright, number 11. The normal boiling point of ammonia, water, and hydrogen fluoride increases in the order NH3, so NH3 has a boiling point of negative 33 degrees Celsius, HF, which is 19, and H2O, which is 100 degrees Celsius. So what is the best explanation for this? So if we remember, the strength of hydrogen bonds goes from FH being the strongest, and when I mean hydrogen bond, I mean this. And then comes OH, so the OH hydrogen bond is that. And then the weakest of them all will be the NH hydrogen bond. So we have to think about why the boiling points do this. So let's think about what A says. H2O forms a greater number of hydrogen bonds per mole than NH3 or HF. Now, I don't know, this might actually be true, because if you think about this using drawings, so let me just erase all of this first because it's getting in the way. Let's draw H2O and H2O. So let's put the lone pairs, because remember, hydrogen bonding occurs between the lone pairs and a hydrogen. So according to this diagram, H2O can form 2 hydrogen bonds per 2 H2Os, so we have 2. What about NH3? Now, you might think that NH3 can form 3 hydrogen bonds per 2 NH3s, but that is simply not the case. So let me draw this using 3D bonds, so I'm going to use wedges to show this pointing towards us, this pointing away from us, and this on the plane. And the lone pair is up here. So this is, remember, trigonal pyramidal, so it is going to be like a tripod. Now let's draw another tripod. So another H, squiggly line, and an H. So how many hydrogen bonds can actually form between these two? So what can happen is that this H can be hydrogen bonded to the lone pair here, and that's only 1. Now you're like, wait a second, can't this form a hydrogen bond with that? Well, no, because they're not orientated to the right position, since this one's pointing up and this one's pointing down. So they're not in the right position, so they can't form hydrogen bonds. So we have 1 hydrogen bond per 2 atoms of NH3. Now what about HF? Well, HF is kind of simple to understand. For every 2 atoms of HF, we can only form 1 hydrogen bond, and they have to be orientated in the right position. So let me draw it in the right position. So they have to be next to each other, of course. So let me draw it so that they're next to each other, like that, with the lone pairs and lone pairs. So this would be an H bond, and there would only be 1 of them. So 1 H bond per 2 atoms. So which one can form the most H bonds? Well, of course, water. And because of this, A seems to be the correct answer, since, as we just observed, H2O can form a greater number of hydrogen bonds per mole of water than NH3 or HF. And this makes sense, since for 2 atoms, it can form more hydrogen bonds than for 2 atoms of H. Now let's look at number 12. Which solid has the highest melting point? OF2, MgF2, SiO2, or ClO2? Now ClO2 is actually molecular, so it's going to have the lowest melting point, so that's out. These two are salts, and we know that SiO2 is going to be a covalent network, which has one of the highest boiling points or melting points out there. So I think that even though we have 2 salts here, the covalent network will typically have a higher melting point than ionic salts, and because of that, C will be our answer. Number 13. A portion of the structure of solid potassium is shown below. in what type of unit cell are the atoms arranged? So at first you might think this is complicated, but this is like a structure. The unit cell is the repeating block, and I think what's repeating is this part over here, where we have this nice little cube over there, and this cube has 8 corner atoms and a center in the middle. So I think this will be body-centered cubic, and that's 13. Number 14, a portion of the phase diagram of elemental sulfur is shown below. Which statement about sulfur is correct? So because we didn't learn much about exothermic and endothermic reactions in relation to equilibrium, we will not consider B as one of our answers, so I kind of just gave you that. So it's either A, C, or D. A, rhombic sulfur cannot be sublimed without first converting to monoclinic sulfur. So let's see what this means. It states that rhombic sulfur cannot sublime into the gaseous state without first going through monoclinic. Now that's not true, since over here, rhombic can go into gas just like that, and because of that, A will be out. Now let's look at C. Rhombic sulfur is denser than monoclinic sulfur. So if we remember from our phase diagrams, we remember that for a positive slope between the solid and liquid phase, this must mean that the solid is more dense than the liquid. Now, if the opposite happens, where the solid is actually less dense than the liquid, then you have a negative slope. So let's label the gas there. In this diagram, we have to compare rhombic and monoclinic, and it looks like the boundary between rhombic and monoclinic is positive. And just like how this is positive, if solid is more dense than liquid, as here and here, then that means that rhombic must be more dense than monoclinic, as shown here and here. And this must mean that C can be a correct answer. But let's not forget D. D says at 1 atmosphere's worth of pressure, or at 1 atm, or at atmospheric pressure, monoclinic sulfur cannot be in equilibrium with liquid sulfur. So let's take a look at this. At 1 atm, so 1 atm is over here, it says that monoclinic sulfur cannot be in equilibrium with liquid sulfur. Is that true? Well, let's think about this. Monoclinic is here, and liquid is here. Can they be at equilibrium at 1 atm? Well, yes, they can. Remember, the equilibrium between two states occurs on the boundaries, and it just has to cross the boundary here. And since at 1 atm, it can actually cross this part of the boundary, that means that monoclinic and liquid form can be at equilibrium, because it can be over here and it would be at equilibrium at atmospheric pressure. So that means that D is out. Let's do number 15 now. The natural logarithm of the vapor pressure in bars of HCN as a function of the reciprocal of the absolute temperature is plotted below. So we have ln of P on the y-axis and the reciprocal of the absolute temperature over here. And it wants us to find the delta H of sublimation of HCN. So if you remember, sublimation is the conversion of a solid to a gas. And this graph over here, where you have ln of P and 1 over T, looks eerily familiar. This is actually the Clausius-Clapeyron equation in its line form, and this is the equation in its line form. And if you remember, we used the delta H of vaporization, which is involving liquid to gas. But this time, we are looking at the conversion from a solid to a gas. So what you have to do is adapt the equation to make it, instead of delta H of vap, you'll make it delta H of sub. And it still does the same thing. It's just that you're describing the process of converting the solid to gas. So, same idea, but different delta H's. So let's now figure out what this question is asking. It wants the delta H of sublimation. And if we remember, the delta H of sublimation can be found by looking at the slope. The slope seems to be negative 4544, so negative 4544 is equal to the slope of this graph. So the slope is negative delta H of sub over R. And since they want it in kilojoules, we are going to use 8.31 times 10 to the negative 3. And when you pull out a calculator and you go negative 4544 times 8.31 times 10 to the negative 3, we get that the delta H of sub, and of course we have to multiply by negative 1 since there's a negative 1 there, then we get that the delta H of sub is going to be 37.8 kilojoules per mole. And the answer that corresponds to that is going to be C. So that's all for this video. Have a wonderful day, everyone.